Okay, so thank you very much for coming this highlight lecture named ADRAS-J First Encounter with Space Debris. So firstly, I will talk a little bit about the overall framework of our JAXA project to pursue the realization of active debris removal. And then Chris-san will talk detailed in depth about the ADRAS-J and what have done in orbit. So as you know, that the number of space debris is increasing, and in particular, the number of tiny space debris is quite a serious problem. And so now it's very important to take many actions to do some space traffic management in a very broader sense. So one thing we would like to take action. So one of the very important actions is this. So to control the future generation of tiny space debris caused by catastrophic collisions, it is effective to remove large space debris from the crowded orbits. So this is a way we are going to pursue to control the generation of very tiny space debris at a very dangerous altitude of the orbit. So JAXA has started the dedicated program to do the active debris removal technology demonstration, named the Commercial Removal of Debris Demonstration, CRD2. Well, by the way, so why active debris removal is so technically challenging? That's because space debris is non-cooperative. So what does non-cooperative means in this context? So for example, the very typical cooperative target like International Space Station has functionality like attitude control and communication and GNSS navigation and fiducial markers and laser radar reflectors and also docking mechanism. However, typical non-cooperative target like space debris does not have any of these functionalities. So that's the reason why it is very hard to even approach or mostly to capture or tow or release that space debris in orbit. So because of these technical challenges, we decided our CRD2 project structured into two phases, one another. So in the phase one, the demonstration spacecraft demonstrated the technology of rendezvous and proximity operation towards non-cooperative target space debris and do the investigation of the space debris. And in the phase two, in addition to the activity of the phase one, the demonstration spacecraft needs to actually capture and also lower its orbit from its original altitude. And also very unique point of this CRD2 project is, so to say, the private public partnership. So under this new partnership type contract, JAXA does not develop or operate spacecraft. But JAXA defines the service specifications and safety requirements, and then private sector design, manufacture, test, and also operate. And in addition, business development also. And in return, JAXA provide technical advices and also dedicated provider technical facilities and also provide their intellectual properties from the research and development activities in JAXA. And Astroscale-Japan has been selected as a partner company for both CRD2 phase 1 and phase 2. The target space debris was very carefully selected, and this is the target space debris of the CRD2 project. This is the H-IIA upper stage. The size is 11 meter long and also 3 metric tons. And so it has been in more than 15 years in orbit. So this is very actual large space debris. So what the demonstration spacecraft needs to perform on orbit for this CRD phase 1 project? There are actually 4 services to be performed. One is the service to do a rendezvous to the non-cooperative target space debris. And the second one is fixed point observation service, which means the spacecraft need to control its relative position to the space debris very precisely and take images for a while. And the third one is the fly around observation service, which means the demonstration spacecraft need to fly around and continuously take its space debris images. And the fourth one is the spacecraft need to lift the proximity of the space debris and goes to the safe disposal orbit. So what is the intention behind of these 4 services to be performed? Actually, there are 2 reasons, 2 intentions. The one is the acquisition of full-range non-cooperative rendezvous and proximity operation technology, which is applicable to a variety of on-orbit servicing missions. So what the full range in this context? Actually, we prefer the right side of the slide, and we actually did not prefer this type of mission design. So it means that the full-range rendezvous capability must include these. So first one is targeted launch capability to make injection orbit very precisely align with the flying actual space debris. And the second one is the capability to do a large deltoid maneuver to collect its orbit align with the space debris. And the third one is capability to bridge the gap between the absolute navigation to relative navigation. And actually, it is the most, I think, crucial if the target is non-cooperative one, because it is extremely difficult to achieve very stable relative navigation in the a little bit far range to the target. So the transition capability from absolute navigation to relative navigation using optical sensor is quite a crucial ability which must be included for the full range demonstration. And the last one is, of course, the proximity operation capability for the non-cooperative target. And also, the second intention was to collect unknown important information about the target. So it means that we did not know much about the target. And if we do not have much information about the dedicated target space debris, it is extremely difficult to do the phase 2 because we need to capture and tow that space debris. So in the phase 1, it is very important to acquire this information by images like attitude motion or surface material conditions or infrared radiation or mechanical condition of potential capture points. So that's the second intention we set the 4 services. And to do this technically challenging mission, JAXA provided a very intensive and also in-depth technical support. Like we provided over 200 technical advice, mainly about rendezvous and proximity operation, and also satellite development. And also, it includes the research and development of the angles-only navigation, which is, so to say, the very important key technology to bridge the gap between the absolute and the relative navigation. And in addition to this, we developed a large-scale motion simulator facility, which enables the demonstration spacecraft guidance navigation system can be verified on ground in the hardware in the loop system, hardware in the loop simulation. So this, excuse me. So this is the dedicated facility SatDyne for this large-scale closed-loop simulation. And additionally, JAXA did several research and development in terms of a rendezvous and proximity operation to the non-cooperative target space debris. So for example, infrared image simulator or LiDAR image simulator or thruster plume impingement detumbling technique or something like that. So that kind of intellectual property also provided to the private sector. Then, in the end, the state-of-the-art demonstration spacecraft, ADRAS-J, has been developed by Astroscale-Japan. So this demonstration spacecraft, of course, has a capability to do full-range non-cooperative rendezvous to the space debris. And so in advance, I get to the conclusion. So actually, the ADRAS-J did a very great job and satisfied all the 4 services. And then, successfully acquired the full-range RPO technologies and also got the very fantastic space debris images, which reveal the unknown information of the space debris. So now I would like to have Chris-san to talk about the ADRAS-J and what actually happened on orbit. It's a very substantial, remarkable performance in orbit.
Thank you, Toru-san. And thank you to everybody here for staying so late. It's almost reception time. So the fact that you're here at the end of the day on Wednesday means a lot to us. Thank you. So before I start, I would like to give a lot of recognition and appreciation to JAXA. This was a groundbreaking mission. It was a very forward-thinking mindset that JAXA had to even put this forward. To allow the private sector to bid on something like this took a lot of creativity and a lot of trust. And we all know in this room and at this conference that the issues of space security and sustainability are paramount. And it is going to take this kind of forward thinking from governments and space agencies and a lot of the cooperation with the private sector to make this happen. And I applaud Toru-san and JAXA for all of the incredible work that they did to get this mission moving. So I will talk about the mission. If you were paying attention to what Toru is saying, I'm going to go over a lot of the same things and just tell you in a little more detail and show you some images about the proof that we're able to show with the mission that we provided. Before I get into the details of ADRAS-J, though, let me give you a little background about Astroscale. I think many of you know Astroscale. You should stop by our booth. If you don't, we've got a nice booth, number 46, so come by and see us. But we are an on-orbit servicing company who has focused on servicing of satellites in orbit. The vision that we have for our company around the world is the secure and sustainable development of space for the benefit of future generations. We need to have long-term sustainability. To do that, we need to have long-term security in orbit, and we are there to provide that. Our mission that supports that vision is to provide this trusted and value-driven on-orbit servicing solutions through a local commitment and global scale. We recognize that everyone wants sovereign capabilities around this technology, but we also know that this is a problem that we cannot solve without global coordination. And that's something that we at Astroscale have thought about from the beginning of the founding of the company in 2013. We were founded by a Japanese individual living in Singapore, founded there, but really got started in Japan. And we've expanded from there. We knew that being in one country alone was not going to be enough to solve this problem. So we expanded to multiple countries, 5 around the world, each of which has coordination, communication, and connections with local decision makers, governments, supply chains, and that is a coordinated effort around the world. And that's something that we at Astroscale provide and we think is going to be essential to making sure that this on-orbit servicing ecosystem is successful. As far as the specific mission areas where we are focused, there's 3 that Astroscale is focused, all of which require rendezvous and proximity operations as the core technology. The first of these is inspection, identifying an object in orbit, understanding its core properties, understanding where threats are, being able to provide this information to clients. That's the core first capability. The second one is servicing. If there are clients that are still active, that want to continue their service through a boost, if they're in GEO, through a boost or in LEO, through refueling capabilities, eventually through repair capabilities, we are able to provide that service. And the third capability is maneuvering, removing satellites, moving them to different orbits, bringing them down into the atmosphere to burn up. Those are the core capabilities that we're going to provide to drive sustainability through on-orbit servicing. And today, we're talking about CRD2, which is around inspection. That's ADRAS-J, what you just heard about, and ADRAS-J2, which we won't talk about here, but as Toru-san said, ADRAS-J is the precursor for a removal mission, which is ADRAS-J2. So, rendezvous proximity operations, this is the core to all aspects of on-orbit servicing. Toru-san went through these already, but really there are some key aspects that I'm going to go over about what we did with ADRAS-J, the launch, the identification of our client, and absolute navigation to get closer, switching over to relative navigation. As was said, that is a key capability, especially when we're talking about approaching a non-communicative, non-cooperative piece of debris in orbit. We need to be able to switch from absolute navigation on the ground to relative navigation on the onboard computers. And then coming in close for inspection, rotation around the client object. And then we didn't do that 5th section here, but capture. And that's what we're going to be working on with multiple missions around the world going forward, including ADRAS-J 2. There it is, beautiful picture of ADRAS-J, which Toru-san also showed earlier. And some background about ADRAS-J you can see here, about 150 kilograms mass, with its wings extended, with its solar arrays extended, it's about 3.7 meters long. It has an RPO technologies and sensor suite, and a sensor suite payload with IR, infrared, LiDAR, and VisCam sensor suite to be able to identify the client object at various points. One of the core things that we built into this was safety. We all know that that has to be a key aspect of any mission, and that was something that we thought about in relation to our client, in relation to other objects in orbit, and in relation to the servicer. So for the client, we had a combination of a passive safety trajectory and an active abort built into the onboard computer systems to make sure that we would protect the client, and I'll talk about that in a little bit. For other objects, we have active collaboration with other objects in our orbit. We are working with ground-based SSA providers and other spacecraft to make sure we are constant communication around where we are. And for the servicer, we had a robust failure detection, inspection, and recovery plan put in place. And we also, as Toru-san mentioned, are bringing it down to an orbit where it will decay within the allotted time of 5 years. So, going through these main aspects that are essential to RPO, it starts with the launch. And we have to call out our Rocket Lab friends. If they're in the audience, I'll say thank you. I already have said so many times, but the insertion was excellent. We launched from New Zealand in February of last year, and were placed into an orbit which allowed us to efficiently and effectively pursue the mission. And there, I think, will be a video image. There it is, the deployment of ADRAS-J. It was early in the morning in February 18th of 24. I was watching from Japan, and it was fantastic to see such a beautiful launch and to hear about such a wonderful deployment. Up and commissioning were completed as planned nominally. From the far-range approach, we were using the absolute navigation. So we closed to within about 1,000 kilometers relative distance between the servicer and the client. We optimized the delta V that we had with the propulsion that we had on the servicer using ground-based SSA for the client, and also GPS data for the servicer. And we also used that angles-only navigation capability that Toru-san talked about. This involved a lot of cooperation between our operations teams in the UK and Japan, our flight dynamics teams working in concert to make sure that they could identify where the servicer was, where the client was, and make sure that we could approach in a safe manner. As we got closer in, we switched to the onboard cameras to use relative navigation to bring us from a few kilometers to about 50 meters of relative distance. You can see some images here from the IR cam, and we also used a combination of the IR cam and the LiDAR to get some additional images that you can see there. And so that transition over from absolute to relative navigation, it's something we also demonstrated on our first mission, ELSA-D. We improved that capability and did it again here. Again, core capability for any approach to a non-cooperative object. And from that point, we did a fixed point observation to get a status of the client. So you can see on the left side, there's a video you'll see, that is the approach into 50 meters behind the client, bringing in that exquisite image of the client there, and you can start to see some real clear details about the status of it. And then as we got to that 50 meters, the next key step was the fly around. Again, a core capability, especially if we're talking about an object in orbit which is rotating. In each of our first 2 missions, we built in the capability with our thrusters on board to be able to circle around a client in case it was rotating. We want to be able to find the right capture point. And when it is rotating, we want to be able to move around and do that. We use chemical propulsion to do that. We had 12 thrusters on ADRAS-J to be able to give ourselves a fine coordination around the client object. As mentioned, we had to do that 3 times as part of the JAXA contract. So we did it both around east to west here, north to south, top to bottom of the object. 3 different times we performed that during the life of the mission. And we got some incredible images. One thing we found was that the client object was not rotating. We thought it might be, but when we got up there, we realized that it was directly pointing down to the Earth. And so we still tested the fly around as contracted. And the video that you'll see now, it looks like the client object is turning. In fact, that is us. That is our ADRAS-J servicer spacecraft flying around the client. So there it is, the picture close in. You can see very clearly the background of what the object looks like. You can see some of the MLI starting to fade off. As it spins around, you'll see the nose cone has some small dents in it, and the teams look very closely at this and are seeing very clear understanding of what the object looks like. As you see the fly around now, it comes up to the payload adapter ring, and you can see that is where we're going to be capturing with ADRAS-J2, the same client object. But you can see that this is coming, and when you see the Earth do a little photo bomb and back and get a nice picture there of the Earth in the background, you can see that is us that is flying around the object. It is not that the object is moving. I've seen that image maybe 100 times, and it always looks so cool. I love to watch it. It's incredible. And it's an incredible step toward driving toward an on-orbit servicing ecosystem, toward being able to grab objects like that and get them out of the way and assure sustainability going forward. To be able to move objects to different areas, to be able to take pictures like that is exactly what's going to be needed for all of us to realize what we expect is going to be a multi-trillion-dollar space economy. But for all of this to work, we also have to build in safety into the mission. And one thing I notice at any of these conferences is we all talk to each other about how great we're all doing, and we all talk about the successes that we've all had, but I think it's also important to recognize that, of course, space is difficult, and that aborts happen, and that anomalies happen with missions, and we have to be prepared for when those anomalies do happen. And so we were, and those anomalies, aborts, did happen. So during some of our approaches into that close-in fly around, we would move in. This is a bit complicated of a slide, but if you follow the green lines, you can see that we moved in a nominal approach. We got to within 50 meters of our client object. We began the fly around, and then our onboard computers detected an anomaly and aborted automatically and moved into an abort trajectory about 100 kilometers in front of the client object. We had a reapproach plan. This was all part of the mission in advance. And we know that a timely recovery is essential in missions like this. On-orbit servicing, we're going to learn as a community that on-orbit servicing is going to be something that needs to be taken care of quickly. We're seeing that in some of the requests for missions that are coming up now, that when there's a problem that's recognized, we need to be able to launch and service it and identify it quickly. The same is true in orbit. And so after the anomaly, the recovery that we made took between 4 and 8 hours. We moved into that 100 kilometers in front of the client object, assessed how we were, we moved back, and within about a month, we had followed the blue line back to our original location, and we took a reapproach again in less than a week. This is key. It's key to recognize that these things happen. It's key to recognize that we're trying to take preparation to make sure it does as little damage as possible and that the mission is still able to proceed. So, summary and lessons learned from this groundbreaking mission. First of all, with ADRAS-J, we demonstrated those core technologies for satellite servicing. The rendezvous, the prox-ops, the proximity approach, the prox-ops on these non-cooperative objects, something that hadn't been done before by a commercial company. We tested out these sensors, verified them on orbit, that allowed a safe approach to the client. We were able to correlate the optical observations from the ground. We gained an understanding of the client object, the core necessity for these kind of inspection missions. We understood its attitude motion, that it wasn't spinning. We understood the condition of the client object, understood the capture point. And this is key for our ADRAS-J2 mission. We could take a very clear look at that payload adapter ring, understanding what it's going to take to go in and grab that when we do ADRAS-J2 in the near future. Understood assessments of differential drag. These are just some of the higher level capabilities that we were able to ascertain about the client object from the mission. As noted, we demonstrated the safety features that were built in for the servicer and our operational capability to make sure that they were implemented. As I mentioned at the top of my remarks, we highlighted the importance of the core partnership between governments, space agencies, and commercial players. Again, this is going to be essential to make sure that this works in the future. We need to work together to make this successful. And all of these, every one of these things, these bullets on there, from safety to cooperation to technical capability to understanding your client object, that is what is going to make the on-orbit servicing sector successful. That is what is going to make our orbits sustainable and commercially viable. So, thank you very much for all of your time. As the moderator said, Julia said at the beginning of this, we won't be taking questions here on the stage, but I know Toru-san and I are very happy to talk to people as they come up. So we'll be available right here. Please take time to come up and ask us any questions, either now or later. And have a wonderful rest of the evening, everyone. Thank you.